Start whenever. Okay. Again, Steve Skiena. This is, I guess, lecture 5 of CSE 548, the analysis of algorithms. Are there any questions about homeworks or bureaucratic details or anything about the material before I start the lecture? Okay. Yes.
Where can you buy those notes?
Okay. The lecture note situation is this. They are on sale at Basics. Basics is a print shop that's in the basement of the Union. So you go to the Union, they have them. They're like $18 a pop. And they look like they did a pretty good job with them. They're bound and all that. And I'm going to put a copy of the Basics notes in the CS library for people to refer to. But I'd rather you buy one of your own rather than steal the one in the library. That would be a bad thing. There's only one copy. That's all that'll be there. We'll also have copies of the notes that are being, each day's notes after class are being walked over to the library. And they will be available when on the website, okay, as time goes by. Some people have had problems with reading the web, the web copies of things. Are there any people in the CS department who've had problems reading the postscript? I'm just trying to figure, reading the postscript. Okay, is there anyone who successfully read the postscript of the notes? Okay. So that tells me that if you're having problems, presumably it is your local Netscape or web implementation that's causing trouble. Okay. Yeah.
I had a problem reading it in math lab, but I didn't have a problem reading it in.
Okay, then presumably if you're having problems, it's now your problem. Okay, because it's not. Apparently, I've set it up so people can read it, and it's just a question of that things may be messed up over at math. So bother the guy who's the system administrator at math. Maybe them get a more update version, and things should work. Okay. Any other questions about the homeworks? Homework 1 is due today. If you're watching this in TV land, make sure you turn in the homework. If you haven't contacted me and you're taking the course remotely, please give me a call or send me email so I know that you exist and that you're indeed keeping up. And if for anything else, we've got Pizza with the Prof on Friday. Slots are filling up, but a few remain, so sign up if you're interested. Any other questions about homework and stuff like that?
Yeah, the sign-up sheet is still out there?
Sign up with the Pizza with the Prof is on my door. So you have to come by my office door. And so that's a good hint. People can find it there. Okay, any other questions? Okay, very good. The thing I'd like to start out with before we get into it was the problem of the day. The problem of the day is, last class we talked about why we like to sort things, okay, why sorting is a good thing, and started to talk about, heap sort, which is a useful sorting algorithm. The problem of the day says, given that you've got a set of integers from 0, you've got a set of integers, okay, 0 to n, where one of these integers is missing. Okay? And you'd like to figure out which one it is by using order n queries of the type, is bit j in the ith number? Okay? So in this problem, we're not making any assumptions about whether those integers are sorted. We're not assuming anything about the integers, other than we've got the set of integers, one of them's missing. We'd like to find out which one it is. Okay? And we're only allowed a linear number of bit operations. Now, why is this a hard problem? Okay, first of all, you say there's n integers, you're allowed a linear number of operations. The trick is to see that each number, if it's written in binary, has log n bits. So there's n log n bits of the input, and we're only allowed to look at a linear number of them. So if you say something like, well, add up the numbers and tell me which one's missing, well, adding up the numbers meant you looked at every single bit. Okay? Or sort the numbers and look what's missing. Okay? Well, so what can we do? The trick is we have to find some way of doing this that doesn't read, that finds the missing number without reading the entire input, which seems like a hard thing. The other thing to look at when you're trying to figure out how do you solve this problem is to make sure you see what it's asking for. It doesn't ask for an algorithm that necessarily runs in order n time. It asks for an algorithm that runs in order n bit operations. Okay, so one dirty thing, which you might consider doing, okay, is using more time to save the number of bits that you read. Okay? There's nothing in the problem that forbids that. Okay? And we've got to be willing when we read these problems to keep our minds open to technicalities like that. Okay? So how would I solve this problem? Okay? My thing would be to try to do is I'm going to try to figure out what the number is one bit at a time. Okay, I'm not allowed to read whole numbers because, well, I can read whole numbers, but they're going to cost me log n bits. Okay, I couldn't read all the numbers completely. But what I can do is check all the integers that are there, all the numbers in my array, and find out what the last bit of each one of those numbers is. Now there were n numbers in the originally. One of them is missing, so maybe I've got n minus 1 numbers there. There's n minus 1 bits, okay, that I'm going to look at. Some of them are going to be 0 bits, some of them are going to be 1 bits. By counting which one I'm missing, okay, if I had all the numbers from 1 to n, I'd expect a certain number of zeros and a certain number of 1s. By counting which one I'm missing, okay, I now know what the last bit of my number is. Okay, does everybody agree with that? Okay, good, people agree. Well, now that I've got the last bit of the number, what can I do? I now know that there are n over 2, I now know the last bit of my number. I want to try to figure out what, and I know what the last bit of the missing number is. So I know the missing number is one of n over 2 numbers that had that missing bit, correct? Okay, if I know what the last bit is, the one that's missing has to be one of those n over 2 numbers with the missing bits. Why don't I now look at the next to last bit of all the numbers that had the right bit as the missing bit? Okay, now I'm looking at n over 2 bits, okay, namely the next to last bits of all the numbers that could possibly be the missing bit, that shared the missing bit in common with the one that, shared this last bit in common with the missing one. By looking at that next to last bit and seeing whether what I'm missing is a 0 or a 1, I can now find the next to last bit of my missing number. How many people follow that? How many people don't follow that? Okay, a majority. Okay, what's the idea? Suppose I'm missing, let's say my 4 numbers, the 4 possible numbers. Actually, okay, this is presumably unreadable, but let's zoom in, where it'll presumably still be unreadable. Here are the 4, let's say 4 numbers, the 4 possible, let's say, binary numbers. Suppose, let's say, this one is missing. If I look at the last bit of all of these numbers, okay, what do I know? Okay, I know that there are supposed to be an even number, same number of 0 or 1s. Okay, if I counted, there were 2 zeros and 2 1s. Therefore, the missing number had to have a 1 as a last bit by process of elimination. If I looked at all the bits, I would expect same number of zeros, same number of 1s. There's more zeros, less 1s. I'm missing a 1. Okay? Question? Well, if not n is even, I can look at all the numbers and know how many I expect. Okay, if n isn't even, then I'll know how many I expect. And there's going to be somebody who's missing. One guy's going to be caught short. Okay? So now I know that it's a number that begins, a number that ends in 1 that is a missing number, correct? How many bits do I have to look at in the second column? Okay? I know that it's a number that is missing that ends in a 1 bit. If I look at this bit, and that bit only, that's enough to tell me what the missing number is. Right? Because I know the number had to have ended with a 1. I know the only possibilities are it's either a 0 or a 1 here. If this bit is a 0, the one that's missing had to be a 1. So the important thing to see here is I only have to look at half as many bits as I looked at the previous time. That's the slick thing here. Okay? Half as many bits as in the previous time. And once I've got the next to last bit, I only have to look at half as many bits to get the third to last bit, fourth to last bit, fifth to last bit, ... Okay? What's the conclusion? Okay? What I'm going to be doing is solving a problem where the number of bit queries I make, okay, for n input numbers is going to be, I'm going to look at n bits and then cut my problem in half. Okay? And this is a recurrence relation, which if you want, you can plug into your master theorem and see there's going to be linear. If you don't want to plug it in your master theorem, you should still realize that it's sort of a geometric series. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, 1 plus 1/32, dot, 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 adds up to be 2. Okay? So it converges to a constant. The series conversion that you've got here is the algorithmic equivalent of getting something for nothing. Okay? Even doing all these stages, looking at n bits and half the bits and a quarter n bits, really costs us the same as just looking at all the bits, the nth bits once. Okay? And that's how we manage to get the linear algorithm. Okay? It's pretty, this is a tricky problem. But the important thing to see here is how the series conversion, okay, ends up saving the day and enabling us to look at less things. Okay? And that the problem that we manage to divide the problem in half each time comes to our hand. That's sort of something we always want to try to do. Okay? Question?
We assume that this series, that this array can have only one number missing.
Right.
And it's like 1 to 4, it can be 1 to 5 or something like that.
Right. We're assuming that now, what we're assuming, if I read the problem, the way I read the problem, okay, it says find the missing integer from 0 to n. So there's the missing means 1 missing. Okay? And that the numbers are limited from 0 to n. So you knew what the numbers were in advance. Okay? And so you knew which, so you could, the goal was to figure out which one was missing. Okay? Any questions? Yes.
Is the array in sequential order?
Doesn't matter whether the array is in sequential order.
If it is, then what I thought was that the last bit will alternate between 0 and 1. And that when you get to a pair that's next to each other that's equal, has the last bit the same,
right.
You know that there's missing, then the one in between, what it was supposed to be, is the missing.
Okay. The question was what happened if, let's say, we assumed that the thing was sorted, the numbers were sorted, and the observation was that you could do it with a linear number of bits in a different way. Actually, if the bits were sorted, I claim you could do it in less than a linear number of bits. I claim you could do it with a logarithmic number of bits. Why is that? Suppose, let's say, let's zoom it up here. Let's make some more blank space. Suppose, let's say, we had, these numbers were all sorted. Let's say we're missing one of them. Maybe. No. Oh, actually, I guess you're right. I guess I should put the numbers there. Yeah. Okay. Let's say there was some numbers missing. What you could do is you could check the couple of numbers, the high order bits, okay, of the two numbers that were right around the middle point. If these numbers were sorted, you would figure out the high order bit of the number that was deleted. Okay? And so by doing two comparisons, you've thrown away half the numbers. And by doing this recursively, you could by doing two comparisons, one or two comparisons right at the middle, you could throw away half the numbers. So if they were sorted, in fact, you could use a logarithmic number of comparisons. Okay? But the problem asked, assuming it wasn't sorted. Well, if it was, then if you did it in linear, that's right. That's reasonable. Okay? But again, we shouldn't assume things that aren't in the problem. That's sort of a general rule. Yes, question?
Did this problem ever arise somewhere?
Well, the question is, does this problem arise? First of all, I think it's a good exercise to realize what kind of things you can and can't do. The problem of identifying a missing integer, okay, does actually come up sometimes. That let's say you have a credit card, okay, and you want to figure out which credit card number they've stolen, maybe. So the idea of finding a missing integer is perfectly a reasonable thing. The question of why would you want to do it without actually reading all the numbers, that's probably that I would say is probably unlikely to occur in common practice. Although conceptually I can see it forming the basis of other algorithms. Okay, but basically this is a good exercise for thinking, rather than I won't insist this is a practical algorithm. Okay, any questions?
I didn't understand that last, how you could do it.
Well, let's try to do this inductively or something like that.
One test is enough. Take the last one before the switch.
Okay, what's the basic idea? You have n numbers, the numbers are sorted. If they're sorted, what do we know about the highest order bit? Okay? The highest order bit, all the zeros are going to be together for the first half. Then they're going to be all ones after that. Okay? So looked at right around the boundary. If all the numbers were there, you knew that the n over second, maybe floor of n over second number, would be a 0 there. The ceiling would be n over a 1. If one of these numbers is missing, you'll be able to see there's going to be either they're both going to be 0 or they're both going to be 1. Okay? Now you've thrown away half the numbers as a missing candidate, and you simply repeat the idea. Okay? Okay? It's good. Okay. What I wanted to talk about, I wanted to start by finishing off some of the stuff we were talking about last class. Last class we were talking about heap sort. Okay, actually we're talking about heaps. Okay, and I don't think we really got to the point where we actually said what heap sort was. Okay? A heap, remember, was an ordering of the elements such that the parent element was bigger than all the elements below it. Okay, and it was a nice balanced tree with that property. Okay? What heap sort does, it's an algorithm that sorts things using this sort of property to do things efficiently. First, it builds a heap. Last class, we showed that by analyzing heap sort carefully, in fact, you can show that building a heap takes only a linear amount of time. In a trivial way, we showed that it would take a logarithmic amount, n log n. But in fact, the careful analysis showed, in fact, it was only linear. Then what did we do? We know that the smallest element in the heap is going to be at the root. So let's take the root element and, or let's say, depending on what order you build the heap in. The top element on the heap is going to be, let's say, the last element in sorted order. So we can pluck the head of the heap out. Okay? We know that's got to be the biggest, or depending upon how we ordered the heap, the smallest element in the data set. Throw that at one end of the array. Take the next last element. Okay? Put that back into position. So take one of the leaf nodes from the heap and put that back at the root. What's that going to do? Let's just make a little picture. Okay? Here we had a heap, and the biggest number, let's say, was 100 here. Okay? We pull out 100, say 100 is the last thing in sorted order. Can't see. Okay, thanks. We then took the last leaf, which here might have been 5. We could take this value 5, stick it in the part of the heap where the 100 was, and then delete it from here. What did that do? This is still going to be a heap. This is still going to be a heap. And we've got some element here up top. We can now call the heapify routine we showed last class to take this element and percolate it back down to its proper position. And thus what we had, if we started out with a heap of size n, after we do this, we've deleted one element and remade the heap. We have another heap of size n minus 1. So we can keep doing this, pulling off the largest remaining element, sticking it into its proper position. The time that it takes is going to be n times through the loop. The swap costs constant time. This costs constant time. The heapify costs the height of the heap, which was log n. So we've got n iterations. Each iteration is going to take log n time. The total time to do this heap sort operation always has to be order n log n. Okay? Any questions about that? This is something to feel in your bones. Okay? Why is it that heap sort has to be n log n? The key operation is the point is we're doing n operations, each operation of which is heapify, percolate it down. That takes time proportional to the height of the heap. The height of the heap is log n. Thus, heapify is an n log n algorithm. Okay, any questions about heap sort or why it's n log n? Question?
Is it also n log n for the average time?
Well, it's n log n in the, certainly in the worst case it's n log n. Okay, that should be very obvious. In the best case, okay, what should it be? Well, in the best case, you might conceivably be able to make it linear, I guess. But the answer is in the average case, it's definitely n log n also. In fact, actually, in the average case turns out to be very close to the worst case. Okay, but it doesn't matter because the worst case is n log n. So we're quite happy with that. Okay, but showing that probably takes a little bit of analysis. So what would heap sort look like? It's sometimes very interesting to try to visualize these data structures using what are called animations, algorithm animations, movies. Okay? Again, this is very much a video course, so we should be looking at movies of algorithms in action to get an idea of what's actually happening. So what is the heap sort movie going to look like? The heap sort movie is, we're going to start out playing the lead role here, is going to be a permutation of things. Okay? What is a permutation? It's an ordering of items. The x-coordinate is going to be where are the items in order. So the first item in the array is here, the last item in the array is here. The y-coordinate is going to be the relative value of that item. So if we're sorting the item, a permutation of the items 1 through n, there's going to be n spots here. This is going to be the index of the array. The y value is going to be the value of the element in that position. Okay? So ultimately, what should sorted order look like? Okay, see if you understand the way the movie's supposed to end. Yes?
Either ramp up or ramp down.
Right. Because when the items are sorted, the ith value is going to be I. Okay? You know, the first element in the first position, the second element in the second position. So when they're ultimately sorted, you would expect to have a nice, okay, diagonal line is the way to picture what's going to be happening here. Okay? How many people see that? How many people don't see that? Okay? Well, think about it, that you've got the numbers here. Okay? You've got, here's a way to see it. Let's see really what happens when we actually sort something. Okay? In doing a heap sort kind of an algorithm, what's really going to be happening? Well, we start out with our elements forming a heap. What we're going to be doing at each iteration is finding the largest element, which happens to be the root of the heap, okay, and it's in the leftmost position, okay. We're going to pluck that thing out and stick it into its proper position in the sorted order. We're constantly going to be, and then we're going to be readjusting the heap to make sure that happens. But the largest remaining thing is always going to be at the root of the heap, okay. So if we keep pulling those items out one by one, we pull out the largest, the next to largest, next to largest, next to largest. If you think about what's happening, we've got a heap that's contracting because we're taking elements out, okay? And we're slowly putting elements in the right position, okay? So we think about what's actually happening when you do heap sort. You start out with a picture of a heap, okay? And then blup, blup, blup. Elements one by one sort of slide out. More and more of them, the heap keeps getting squashed down, 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 and finally at the end it goes away, and the items are left in sorted order. Okay? That's sort of what the picture of what heap sort is really doing. Okay? What we're doing here is we're representing the heap as somehow being elements in the array also. Okay, we're assuming we have the same array that we're using to store the heap and the elements that we're building. Okay? So that's really what heap sort looks like on television. The building heap process. We started out with originally a random permutation. Okay, and then what did we do? We then started percolating, okay, from the bottom. Okay, represent the leaves of our thing. We then started slowly merging heaps out of these things. So if we look at how the heap is shaping up through time, there's going to be a lot of little manipulations on this side as this part slowly gets ordered. But nothing much really sort of seems to be happening very much. Okay? But ultimately, when we end up with a full heap, our full picture of a heap should look something like this. The largest element, finally, is going to be at the second and third largest elements have to be very close to the root. So if you look at it, the very corner of this heap looks very well ordered. because we've got a fairly strong ordering. All of those nodes have to be bigger than everything below it. But as we get towards the right part of the heap, you know, the ordering relationship is far weaker. Among the n over 2 children, there's no ordering on them. Okay? So in fact, the picture of the heap that we have there, the order is fairly weak, which is what we would expect. That's why it was so easy for us to build the heap. We could do it in linear amount of time. Okay, any questions about the Heapsort movie? Okay, why it sort of looks like this? Okay, and it ends happily. Heapsort works at n log n time. Okay, very good. Okay, what are the lessons of Heapsort? Well, last class we showed a lesson. One lesson of Heapsort was that we could sort that by doing careful analysis, we could in fact sometimes prove something that looked like it was n log n or looked slow. Sometimes doing careful analysis could make it fast. Okay? The second lesson of Heapsort is that Heapsort is a fast algorithm because we're using a good data structure. Okay? The idea of Heapsort is in fact nothing but the idea that we use selection sort for. Last class I started out with selection sort. What is selection sort? Loop from I goes from 1 to n, find the smallest remaining item, pull it out of the array and put it first in the put it, you know, at the next sorted spot in the array. This is selection sort. This took n squared time. Okay? That's a very simple algorithm. Is there anybody who doesn't understand selection sort? Okay. Here. The interesting thing is that heap sort is nothing but selection sort. Where we're using a fancy data structure. What are we doing in heap sort? We're looping through, we're finding the smallest item, and we're pulling it out of the array and putting it first. The difference is that in selection sort, what we were doing, when we were using an array, to find the smallest element meant scanning through the entire array, which took linear time. Pulling it out and putting it first took constant amount of time. Okay? When we're using a heap, the time it takes to find the smallest element, well, that takes constant time, if you wish. Okay, it's just there. To pull it out of the array and let things percolate down takes logarithmic time. So by using the heap as data structure, what we've really done is we've implemented selection sort. But we're now using n log n time instead of n squared time. The whole reason why heap sort works well is because we've got a clever data structure behind it. And this is a good lesson to keep in mind. Many a slow algorithm can be sped up by just using the right data structure. And in coming weeks, we'll talk some more about data structures. But this is something to take to heart and make sure you understand it. Okay? Any questions? These two algorithms are really the same. That's important to realize. Okay? This heap data structure is an example of something that's really very useful. Okay? It's an example of a type of data structure we call a priority queue. Okay? What is a priority queue? A priority queue basically has 3 operations. Okay? It's a data structure that lets you insert an item into the set. It lets you say, hey, what is the largest item? Okay? And it lets you delete the largest item from that set. Okay? So you could build priority queues in lots of different ways. You could build them by just using an unsorted array. If you did an unsorted array, you want to insert something, well, stick it at the end of the array. Constant time. Find the maximum, linear time, scan through it. Okay? Delete the maximum. Well, what you'd have to do is, you know, if you have a, you know, it depends upon whether you have a pointer to it where it is. And swap it out, swap it with the last element and delete it. If not, what you could do is, and which would take constant time, or maybe if you want to be a little clumsier about it, you could scan through, find the smallest one, and move all the items up to cover the slot. But you could implement it with a sorted array, but much better is implementing it with a heap. If you use a heap, the trickle-up insertion algorithm means we can insert it at the leaf, it up to the top. It'll take log n time. Finding the maximum just means reading the top element off. Okay? And extracting the maximum means basically deleting the first element, replacing it with the last element, decrementing the number of elements, and then calling heapify to percolate that element down the array. Okay, so that could all be done in the height of the heap or log n time. The heap is a better data implementation of the priority queue data structure. Okay, but obviously there's that, and there's more implementations than that available. Okay, any questions about priority queues? What they are? Okay, this is a useful thing. Priority queues are good things to realize. They come up in lots of different problems. Okay, for example, one common place where priority queues come up is in simulations. You've got a, let's say you want to simulate the behavior of an airport. Okay? At certain times, planes are going to have to take off and land. Okay? And certain things happen at strange times in an airport. If a plane comes by and 2 of its engines have died, suddenly its priority to get the access to the runway will increase. Okay? So you've got to be able to, in some sense, when you're running a simulation, keep track of what is the next thing to happen, the next guy to use the landing strip. Okay? So what you could do is you could build a data structure where the priority to the landing strip, okay, is stored in a priority queue. If somebody, the next person to get the landing strip is the person who has the highest priority. And again, you've got to be able to insert new items. Okay? You've got to be able to remove the largest one. These kind of things are basically priority queue applications. Okay? And so they come up quite often in simulations and things like that. Another case where priority queues turn out to be important is in geometric algorithms. Again, this is just an example of why they're important. But in a lot of geometric algorithms, you've got a sort of geometric arrangement of lines. Okay? And you have to make sure you look at all the points. Let's say you want to find out what's the largest area region defined by this thing. What you need is some kind of a systematic ordering to walk over this arrangement to see sort of what are the points that you encounter. And so the usual way to do this is you take these points when you find them, stick them in a priority queue based according to their x-axis value. And then pull these items out one after another. That's going to mean that when you look at them, you're going to be basically thinking about a line that's going from left to right, stopping at each point as it comes by. Blip, 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 blip. And the important thing is to see that end only at these points. So by ordering these values, okay, and pulling out the next leftmost thing, you get a good ordering on these things. And that's really, that's really the heart of making these kind of things work. And the data structure of choice to maintain this ordering is a priority queue. Okay? So keep that in mind, file that away as a good data structure. Okay? One last example of priority queues, just to sort of talk about it, sort of a real practical example that came up in a project I was working on recently. There's in what we call greedy algorithms, we're always looking for trying to find the next best thing to do. So in our particular problem, we had this is a problem that came up in graphics. We had a triangulation, which we wanted, okay? And in order to describe the triangles to the graphics engine, the most efficient way to do it is to find a path to walk along the triangles. So that when you describe each triangle, you only describe the next triangle by its incremental change. Okay? Why you want to do that turns out to be a little bit complicated, but it ends up making the graphics rendering faster because of certain hardware. But what's interesting is we were building in our program, what we were trying to do was we took our triangulation, and our basic idea was find the longest strip, delete those triangles, and then find the longest remaining strip. Delete those triangles, find the longest remaining strip. Well, how did we maintain what was the longest remaining strip? We used a priority queue. We stored our strips in a data structure ordered by the number of triangles they had. And so we quickly say, give me the largest one, give me the largest remaining one, give me the largest remaining one. So really what I wanted was, sorting them by size was unnecessary. All I needed was a priority queue, because I only needed to be able to quickly get at what was the next largest one, and then be able to adjust the list to reflect the values as they change. Okay? I don't know whether this is this sort of clear, or I don't know if that's a good example or not. But these things come up a lot. Priority queues are definitely things that should be in everybody's bag of tricks. And I urge you to put it there. Any questions about priority queues or heap sorts or anything like that? Good data structure. Okay? So heap sort is uses a good data structure and is a good sorting algorithm. But there's other good sorting algorithms. Okay? The algorithm that turns out to be the best algorithm in practice for sorting is an algorithm called Quicksort. Okay? On a different principle than heap sort, but it's also going to achieve the same average n log n time. Actually, it's going to be a little bit better, but it's basically going to be an n log n algorithm. Now, what's the story behind Quicksort? It uses an idea called partitioning to find the smallest, the best item. In heap sort, we were always trying to find the smallest remaining item. Instead, what Quicksort is going to use is it's going to use the idea of partitioning, namely picking some element, okay, and then taking the entire data set and determining which items are before it and after it in sorted order. So for example, here, suppose, let's say I pick 10 as my pivot element. Originally, I had my items, they were in arbitrary order. Afterwards, I've put all the items that are less than 10 to the left of it, all the items that are greater than n to the right of it, and stuck n in the middle. Okay? That's what I mean by pivoting, okay, or partitioning. Okay? And the pivot operation, this partition operation, is the basic step that makes Quicksort go. Okay? Any questions about that? Okay? The key idea behind pivoting elements, the pivot thing, is that all the items less than the pivot are going to the left, all the items that are greater than the pivot go to the right. The key thing about this to remember is, what do we know about where the pivot element actually goes? If I put all the elements that are less than the pivot to the left of it, and then put the pivot element there, what do I know about the position of the pivot element after I've done this operation? It is correct. Okay? What is any element's item in sorted order? It's, where is it? Well, you know, it's going to be right after all the elements that are smaller than it. So by definition, when I do one of these pivot steps, partition steps, okay, I know that I've got one element in its proper position, okay, namely the pivot element. Okay? So ultimately, if I do n of these pivot operations, okay, I will end up with all the items in their proper spots. That's sort of the key idea behind the correctness of Quicksort. Okay? Any questions? Well, how do we actually do this partitioning step? Okay? I mean, again, one way to look at it is to simply say, look, to do the partitioning, you've got n elements. You're going to compare your pivot element against all the other elements. It takes order n time. And that's the way that I would normally think about these things. Pivoting seems to be somewhat confusing, or this partitioning step seems to be confusing. So let's look at a fairly detailed example of how you might actually implement this thing. You might do it by maintaining, in some sense, the array having three sections. The items that we know are less than the pivot, the items that we know are greater than the pivots, and the items we don't know anything about. Okay? So what happens when we try to pivot, for example? If this is our initial input array, originally we have our pivot element sitting here. We don't know any item that's greater than the pivot, so that our right boundary is here. We don't know any item less than our pivot, so our left boundary is here. Okay? What's the idea going to be doing? why don't we take a look at each element, scan from left to right, and see if each item is less than or greater than the pivot, and then do something with it. So if pivot is 10, is 17 less than the pivot? No. So it's got to end up on the right side of our array. What we could do is simply swap the rightmost unexplored element with the 17. Okay? We know 17 is bigger than 10, so we can slide our right wall over to one spot. Our left wall hasn't changed because we haven't found anybody that's less than the pivot. Okay, that's sort of the first step. We could then repeat this thing. Is the first element less than the pivot? Yes. Slide it over. Is the next element 12 less than the pivot? Okay, no, because the pivot is 10. So let's swap 12 and the last number. Is 8 less than the pivot? Yes. So let's move the wall over. Is 6 less than the pivot? Yes. Let's move the wall over. Is 19 greater than the pivot? Nope. So let's swap these two and move the wall over. Is 23 less than the pivot? No. Less than the pivot of 10? No. So we swap it back. We have our two walls have now met. We now know that all of these items are less than the pivot. All of these items are greater than the pivot. And the pivot's been sitting here, you know, in the array. What we can do is now swap the leftmost element of our right bound with the pivot element. The pivot's in its proper position. Everything less than it's in the proper position. Everything greater than it's in the proper position. By making one sweep through the array, we can do the pivoting, the partitioning, in linear time, using a nice simple loop. Okay? Any questions about the partition step? Okay? Question was, how do we choose the pivot element? For now, I'm just choosing the rightmost element. We'll talk more about that later. Okay? In principle, it doesn't, I mean, to a certain extent, it doesn't really matter. We're just doing a pivot operation. Okay? Any questions? Well, what good is this? Where are we now? We know that the partitioning step consists of doing at most n swaps, a loop of going around n times. It takes time linear in the number of keys we have to do it with. What do we get after we've sorted, after we've done a pivoting? The first element thing is, as I said, that the pivot element itself ends up in where it's going to be in final order. So we never need worry about the pivot element again. It's very happy. The second thing we get is that after we've done a partitioning, no element is ever going to flop from one side of the pivot element to the other again. If it was less than the pivot element, it's going to stay less than the pivot element. You know, none of the elements are changing when we sort them. That would be a recipe for disaster in any sorting algorithm. If suddenly elements are free to change during the operation, that would be bad. Okay? But we know that after we've done the pivoting, all the elements to the left are, in some sense, a block that's never going to get separated again. So the second thing we get is that we can sort all the elements to the left of the pivot and all the elements to the right of the pivot independently. We've reduced our problem to now from one big sorting problem to two smaller sorting problems. Okay? And this is exactly what we want in a divide and conquer kind of situation. It's easy to sort small things. If we can break the thing up into pieces, okay, and do them independently, this gives us a recursive sorting algorithm, okay, namely Quicksort. Okay? Any questions about how the recursive algorithm works? Okay? It looks like this. Basically, the top-level loop to Quicksort says we want to sort an array A. We want to, in fact, sort the elements from 1 to n, the first element through the last element in the array. How do we do that? Well, that calls our Quicksort routine. So long as there's more than one element to sort, pick some kind of a pivot element and partition it, and tell me where the pivot ends up. I don't really care what the pivot was, but I care where it ends up. Then sort everything from the low bound of what I have to sort to just before the pivot to just after the pivot to the high bound. my general thing, 2 recursive calls, okay, and I'm done. The basic partition algorithm, I mean, I sort of described it. It's a little bit tricky to code, but I mean, this is it. This is pseudocode. Okay, you loop around. For each one, you test if it's greater than or less than the pivot. Move the walls and swap accordingly. The details you should be able to figure out from what you've done. This is the entire code for Quicksort. Okay, any questions about the pseudocode? No questions. What does the movie look like? Okay. Well, first, let's think about the partition movie. Okay. In the beginning, we've got a arbitrary permutation of items. Here in our movie, the stuff above the, each of these bars is going to represent an item to sort, and the length of the bar represents its size. So this is a big item over here. This is a small item over there. So what is the partition step going to do? Well, maybe you can't see it too well, but in fact here, okay, is where the partition element was. Okay, and all the items that were smaller than that white bar. Okay, again, there is a white bar there if we zoom up in there. There you go. Okay. Every item that was less than it got shoved to the left. Every item that was greater than it got shoved to the right. These are still in some arbitrary order. These are still in some arbitrary order. But we separated them, the big from the small. That's what you want to have happen in the partition. Okay? So that's how the partition works. What does Quicksort itself look like? Well, let's go back to our permutation plots. After we've done a partition, what do we get? All the items below the pivot element in the array are less than that. So you've got what seems like a random permutation, okay, and a random permutation, but these are all the big items, these are all the small items. See, there's a lot of order here because we've got all these regions cleaned out. We now pick our next partition, which happens to be down here. It wasn't so good. But again, that split this big square into smaller pieces. Not much smaller, but it didn't do so good. The next pivot was a nice pivot. Okay, that took this big square here and broke it into 2 squares again. So what you're going to be ending up with is these items are getting forced to the diagonal. That's how we want things to end. But they're getting forced to diagonal in chunks. Okay? And so in some sense what's happening is, unlike Heap Sort, what we get is that basically the story ends by these things just simply getting closer and closer to the diagonals. And so it ends more with a whimper, I guess, than the Heap Sort movie ends. But ultimately it ends with them sorted. Okay, any questions about these animations? Okay? Good to see these things a different way. Okay? So let's analyze Quicksort. Okay? And think about what the algorithm is. You should believe it's a correct algorithm. Why do we know it's a correct algorithm? The pivot element is in its proper spot, and then we're recursively calling sort on each half. No item swaps sides, so every item eventually gets sorted. Okay? The correctness of it should not be in doubt. The efficiency of it is, on the other hand, a much harder problem to think about than correctness. How much time does this algorithm really take? Well, let's look at some examples. Okay? It turns out it depends a lot upon what the permutation of the items was to start with. What would be the best case of Quicksort? The best case of every divide and conquer algorithm, just about, in fact, let's say every divide and conquer algorithm, is when we split the problem into equal-sized halves. The interesting thing to note about Quicksort that's different than most other divide and conquer algorithms is we really don't know the sizes of what we're splitting it into until after we've done the split. If we know that the best case is where we pick an element that's going to be, in fact, the median element, okay, you may say, well, why don't we pick the median element and just use that for our partition? Well, somehow you've got to identify that. Instead, we're just picking an arbitrary element. And so we're going to break it into 2 halves. We want them to be balanced, but we have no guarantees. Suppose we got very lucky, and in fact, we always did end up with the median element. Okay? Then what would the recursion tree for this thing look like? My claim is it would look something like this. You start out with your array of n items unsorted. The pivot element ends up plunk in the right position. It divides the thing into 2 halves, each of which is each of which contains basically half the number of elements. We now, on this side, call the partition element. Plunk, we get the exact middle, splits it in half. Plunk, we get the exact middle, and we're now down to singleton elements. So what is the height of the recursion tree going to be when we've got a perfect splitter each time? Okay, say it loud. Log n. Okay? You've got a tree, you're doing a split each time. Okay? You want to know, you're ending when you get down to singleton elements. You start out with n items. You want to know how many times can I split them in half until I am down to one item. That is the log base 2 of the thing. Okay? And that you've got to feel in your bones. Okay? Now you may say, well, wait, it's not exactly the log base 2 because you're pulling out one extra element. But big deal. It's sort of almost exactly a half split. In fact, it's actually a little bit better. Both sides in a perfect split get to be a little bit less than half. But the main thing to see, the big action, is that we're cutting this thing in half each time. Now, whenever you divide it by a constant fraction, you're going to get a tree of height whose log is going to be dependent upon that fraction. Okay, so if we're splitting it in half, we get log base 2 height. What's the total amount of work we do at each level of this recursion tree? Well, we're going to be taking through this, and then we're going to do a partition step on that unsorted chunk. That took linear time. So here, if there were n elements, we did n total steps in our partition. Here we've got n over 2 and n over 2. It would take n over 2 steps to partition this, n over 2 steps to partition that. The total time is going to be at most n to do the partitioning in both halves. Likewise, we're back in the same situation. The total partitioning on each level is going to be order n. And in a best case, we have log n levels of perfect partitions. Okay? Log n times n is n log n. Okay? And so the best case of Quicksort is n log n. Any questions about that? Okay? Don't be afraid to ask. This is an important thing to see sort of where these trees come from. Okay? And these trees, I think, are really the idea that you need to sort of see why these things are happening, where the logs come from. Logs basically are dead trees. Okay? So you should be clear what the connection is between logs and trees. It's very intimate here. Yes?
Why is the big O of n log n and not the worst case? Because
Oh, okay. Big O, and I'm only talking about the best case. Okay, remember what the big O notation is simply a way for describing a function. I could use the big O notation to count, my bank account. I can use it to count any function. Okay? Here what I'm asking for is what is the time it takes in the best case as a function of n. So I'm showing that, in fact, the best case is, in fact, theta of n log n. It actually takes n log n time. But so the reason here is, you're right, the worst case is not going to be n log n. But I'm saying the total time of the best case as a function of n. Okay? And so the big O is simply a way of describing functions. The function I'm interested in here is the best case time. Any questions? Okay? So that's the best case. What is the worst case for Quicksort? In the worst case of a divide and conquer algorithm, okay, is when instead of splitting things as evenly as possible, we split things as unevenly as possible. Okay? If you think about, you want to get a job done as quickly as possible, and you have 2 people to work on it. Is the right thing to do to give one guy a small piece and the other guy everything else? It is if you're the guy doing the small piece. But if you want to get the job done quickly, okay, you want it balanced. Worst case is the unbalanced case. Okay? So suppose, let's say, when we picked our pivot element, we were extremely unlucky. So instead of getting n over 2 items on each split, in fact, the pivot element we picked happened to be the very smallest element in the array. It could happen. There's no reason why it couldn't. If we did, when we split our tray, we had nothing to the left of it, and n minus 1 elements to the right, but the pivot element ends up in its right spot. So that's a consolation. Suppose we now go again. I want to partition it. And again, you're unlucky. The pivot element ends up being the smallest item, and n over 2, and you now have n minus 2 items left. Maybe next time the pivot element would be the largest element. But that doesn't help you. You still have a very unbalanced situation. So if you got really unlucky, you could end up with a tree whose height is going to be what? Okay? What's the height going to be? N. Okay? Or if you want to be precise, you could say n minus 1. Okay? That's quibbling. Why n minus 1? Well, because in fact, when you're down to one element by itself, one element split, you're never going to want, when you have two elements, if you, in fact, use one as the pivot, the other side is going to only be of size 1. Okay? But that's unimportant. That's just to make sure you understand what the tree really looks like. So if you think about it, in the worst case, we now have n minus 1 levels. Okay? Or n levels, doesn't bother me. Okay? Instead of log n. Each level, we're going to be doing how much partitioning? Well, we're going to have to partition these n elements. That's going to take n steps. Here we're going to have n minus 1 elements to partition. It's going to take n minus 1 steps. N minus 2, n minus 3, n minus 4. If we think about it, on the first, the way I like to think about it, on the first n over 2 levels of this tree, I'm always going to be doing at least n over 2 steps on the partitioning. Why? Because this chunk is simply going to be size n over 2 or bigger. So if I have n over 2 levels, each of which requires n over 2 steps, the total time is going to be at least n squared over 4, or theta n squared. Okay? So in the worst case time, okay, you're in trouble with Quicksort. In the worst case time, it's n squared. Heap sort was n log n. Silly selection sort, okay, was n squared. So judging by the worst case, okay, it seems that Quicksort had better defend itself to justify its name. Why is Quicksort quick when the worst case is bad? Okay? The only hope would be if we could show something about the average case, so that on the average case it's pretty good. Okay? Yes, question?
The few slides before, it seemed like Quicksort would actually, on average, be better than Heapsort.
On
like the sorting thing of choice, but don't you have to do all the recursive stuff while
on average, okay, we'll talk about why is Quicksort and Heapsort better if one's n log n or not. Basically, what's the problem? Why do I say Quicksort is better? The reason I say Quicksort is better is generations of programmers have found that Quicksort runs faster than Heapsort if you implement it properly. Runs faster by a factor of 2 or 3 times. Okay? If you're saying, well, wait, I can't show that in my analysis because all I'm dealing with big O, you're 100% right.
No, even in the best case, it seems like.
In the best case, okay, again, best case, both of them are going to be n log n. Okay, basically, I mean, in the average case, both of them are going to be n log n. Okay, and in fact, the average case for Quicksort turns out to be slightly better than the average case for Heapsort. If you don't believe me on that, you don't have to believe me on that. Okay, but you have to believe me that both of them are n log n on average. I haven't convinced you that Quicksort is n log n on average. But you should believe that the worst case of Heapsort is n log n. Okay, and in fact, the average case is presumably also. Yes?
Could it be that Quicksort, because both sides can be independently calculated, given the appropriate hardware, you could actually implement multi-threading on a multiprocessor system, such that both can be calculated at the same time, whereas in, say, Heapsort, it has to be sequential in the sense that you cannot go on to the next recursive step until you finish that EP5 step.
So the question now is, what about recursive procedures? Okay? And the question now, I mean, what about parallel procedures? Suppose you had a machine that was parallel. Could you, in fact, use an algorithm that would, which algorithm would be better maybe on a parallel machine? And the idea of using Quicksort seems like a better idea because you've broken the problem into 2 separate halves. And so somehow you're saying you sort of give half to one processor and give half to another. In fact, if you're going to split it in halves, there's other algorithms that will, in fact, guarantee that the halves that you get are always exactly the same size. Okay? So, in fact, for parallel purposes, it's clear that you would be better off with Quicksort than Heapsort. But on the other hand, it's also true that if you're really going to do it in parallel, there's probably algorithms that are better than both of them. Although in principle, they both would actually, in principle, they'd be pretty close to Quicksort. They'd be more like a merge sort procedure. Okay, sort of the parallel sorting algorithm of choice. Okay? But I don't really want to go into parallel algorithms in here. Okay? Any questions? Okay? So what was the situation? Okay? We had Quicksort. I'm claiming Quicksort is fast, even though its worst case is bad. Why is that? Okay? The important thing is, I mean, there's two ways you can tell. One is I can give you the exact average case analysis, and you can look at my equations and be impressed and then say, yeah, it's true. Or you can get an intuitive feel for why Quicksort has to be fast, okay? And why Quicksort has to be n log n on average, okay? And that's what I'd like to stress here, okay? Is why is Quicksort going to be fast on average? Why is it if we pick a random pivot element, likely, or an arbitrary pivot element, likely it's going to do a good job for us in partitioning the thing into two roughly equal halves? Well, let's think about it. Suppose we have n items that we're sorting, okay? If they were in sorted order, what would be the element that we wanted as our pivot? Ideally, the median element, the one that would be in the middle in sorted order. Okay, that's what we really would have liked. But if we're willing to have something that's very close to the median element, that would be almost as good. So suppose, let's say we took all our keys and we sorted them. And we took as our pivot element any key that lied between the n over 4th item and the 3n over 4th item. Okay? What is that? Why did I pick those numbers? Well, that happens to be sort of the middle half of the array. 3 halves minus 1/4, 3/4 minus 1/4 is a half. So if we think about it in sorted order, half the items okay, that are potential keys, all would give us partition elements that would somehow split this chunk up. Well, what do we know? If we had picked our pivot element as being one of these items in gray, what is the worst case that we could have if it was going to be a gray item? Okay? Which item? Okay? This one? No. Either that item or that item. Okay? Because that would be the one that would give us the least balanced split. So suppose, let's say, we pick one item at random, and it happens to be in this gray area. We know that if it was in this gray area, the smallest piece that we have left is going to have to be at least as big as n over 4 items. And the biggest piece we have left is going to have to be at most 3n over 4 items. Okay? How many people agree with that? How many people do not agree with that? Okay, everybody agrees because it's true. Okay? So what do we know? If we picked a gray pivot element, okay, then my claim is the largest part of the array that would be left after a gray partition would have at most 3n over 4 elements to it. Okay? Suppose every single time we picked a gray element as our pivot. Wouldn't happen, but let's say we did. What do we know? The worst case for us would be we picked the worst possible gray element. That would mean that each time we took our n items, the bad side of our splits had 3/4 as many elements as it did before. So we start out with n items. Each time we divide it by 3/4, 3/4, 3/4, 3/4. How many times do we have to divide it down by 3/4 till we get down to singleton elements? That's the height of our tree. Okay? Well, the answer is it's got to be a log. What's the log? The log is going to be the log. Let's just think about it. Okay? 3/4 to the L times n equals 1 is the same as saying n is equal to 4/3 to the L. Just sort of multiply both sides by 4/3 to the L. Taking the log of both sides, the log of n is going to be L times the log. Sorry about that. Thank you for that. The log of n is going to be the log of n is going to be L, which is the height of the tree, times this thing. Basically, what we know is that if we use good partitions, any gray partition, the height of the tree we're going to get is going to be at most log base 2 of 4/3 times the log base 2 of n, which is less than 2 log n. So a tree of height 2 log n of only good partitions is going to do the job. Okay? Does everybody agree with that? Okay? But what about bad partitions, you say? Okay? Maybe my pivot element was here. Maybe my pivot element was there. How come you're only counting good partitions? Well, a tree of at most 2 log n levels of just decent partitions will suffice. But if we pick an arbitrary element as the pivot, what is the probability it was in our gray region to start with? Okay? Go back to the picture. We have our elements we said were in the gray region. So half of the elements would give us a decent pivot. What's the probability when we pick a random pivot, it's going to be a decent pivot? Okay? This should be very easy. Okay? 50%. You flip a coin and you either get a good pivot or you don't get a good pivot. Okay? Half the elements are going to be good pivots by good here. Okay? Is that clear? And whenever I always got good pivots, my tree would be of height 2 log n. So what's going to happen in real life if you want to think about it? Okay? What you're going to get in real life is a situation where when we pick a pivot element, okay, 50% of the time it's going to be a good pivot, 50% of the time it's not a good pivot. Fine, we split it into halves. If we had a bad pivot, well, that didn't do us much work. But we know that when we take any path down the tree, approximately half the times we go through pivots, they have to be good pivots. Okay? If you want to flip a coin and end up with n heads, how many times do you have to flip the coin? 2n times. Okay? So in order to get 2 times log n good pivots, I really need to flip my coin 4 log n times. Which means that, counting good and bad pivots, my tree is going to have at most a level, on average, of about 4 log n. Okay? Because I'm at most doubling the number. I'm going to have good and bad levels. And there's expected to be the same number of good as there are bad. You that it has to be a log n thing. Because usually I'm going to get pretty good splitters. Okay? And you have to be incredibly unlucky to constantly pick the bad ones. When it's like saying, well, if I flip a coin, you're right, if I flip the coin 50% of the time, 50 times, it might come up heads, 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 heads. But it won't come up heads, 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 heads. Just like when you buy a lottery ticket, you might, okay? But you're not going to win. Okay? The point is that these things work out the way that they're supposed to. Okay? And half of these things are going to be good splitters. So the level of the tree has to be, the height of the tree has to be n log n. It has to be log n, order log n. The time it takes has to be n log n. Any questions about that? This is important to understand this principle. This is why Quicksort works. There's nothing I did with this half that you third or 2/3 or something like that. But the basic idea, I think, should be clear from this. Any questions? Okay? That's the important thing to understand. I'd like to quickly go through the average case analysis with some more rigor. But if you're confused by what I'm going to do, don't worry about it. The way you have to understand this thing is intuitively. Okay? If you understand it intuitively, okay? So if you're torn between understanding what I just said before or what I'm going to do now, understand what I did before. Okay? But let's work out a rigorous analysis of exactly how many comparisons we would expect on the average case of Quicksort. Okay? The ideas behind this there's really going to be two ideas that are worth knowing or worth understanding. Okay? The first is to see that we can model the average case time of quicksort relation. What is the recurrence relation? Well, we're going to pick, okay, on average, at each level, what's the time it takes to sort using quicksort, where we have n items? Well, it depends upon which pivot we pick as the first thing. The pivot can be any item between 1 through n, or can be ranked any item between 1 through n. Each of them get picked with equal probability. Once we pick a pivot element p, the work that remains is we have to sort all the items that are less than p, of which there are p minus 1 of them. And we have to sort all the items that are greater than p, of which there are n minus p of them. Okay? So the basic idea of this of the recurrence relation is each pivot element gets picked with equal probability. Once we have a pivot element p, the work to be done is described by these two recursive calls. And the work done to get to that point by doing the partitioning is this n minus 1 step. Okay? So we pay a linear amount of time to do the partitioning, and then we have to do the recursive solutions. Okay? And the cases we get, there's n possible cases, each of which occurs with probability 1 over n. That is the recurrence that governs the average case of quicksort. Okay? Any questions about this recurrence? Okay? This is important to see. If you can understand that the recurrence is right, you can just say solve it, and the answer you get is going to be what it should be. So are there any questions about why this recurrence captures the average case of quicksort? Okay, it's doing exactly what quicksort is doing, okay, with the same probabilities that it does everything. Okay? That is the most important thing that goes into the average case analysis of quicksort. The other thing that goes into it, okay, is one useful fact of analysis, okay, which has to do with what we call the harmonic numbers. What are the harmonic numbers? We say that the nth harmonic number, let's try zooming it in, h sub n, is defined as the sum as I goes from 1 to n of 1 over I. So the first harmonic number is 1. The second harmonic number is 1 plus 1/2. The third harmonic number is 1 plus 1/2 plus 1/3, ... Okay? Now, harmonic numbers are kind of interesting because we talked about series that converge. Well, you know that the sum of 1 over I raised to any power is going to converge. Okay? That's something that you learned in calculus. In fact, raising it to the first power is exactly the point where it doesn't converge. Your limits and stuff. So in fact, what really turns out to be true is the value of the nth harmonic number is this. In fact, it's the natural log of n, very closely. Why do you believe this? Well, you actually have seen this. You probably don't remember it, but you've seen it. Remember in calculus when you took the integral as I goes from 1 to n of 1 over I. The area under that curve was log n. That was the definition of the log. Okay? And really what we're doing here is computing an approximation to it, sort of summing up these boxes. The width of the box is 1, and the value is 1 over 1, 1 over 2, 1 over 3, ... So the value of the nth harmonic number is going to be a log. And this you need to know to see where the log magically comes out. The point is we're going to be doing a sum like this, and that's where the log term is going to come out. So if you understand those two things, now on is just going to be algebra. Okay? It's just going to be solving that recurrence relation. Okay? What was the recurrence relation? The recurrence relation, again, just to remind you, looked like this. How do we solve it? Well, you've got here a 1 over n term. You're summing up as t goes to p minus 1, n minus p. If you think about it, you can break that into two separate sums. This sum, the value of the indices go from 1 to n. This sum, the value of the indices go from n to 1. So really, these two sums, if we broke them up into two sums, are summing up exactly the same thing. just in a different order. One's going up, one's going down. So, in fact, we could replace that sum by, instead of having two terms, both of which are the same, we replace it by one term where we just simply take twice that. That's the first sort of move that we do here. Okay? The second move is we multiply both sides by n. Now you've got n times tn here. Why do you multiply it by n? Well, you get rid of that divided by n, which was kind of an ugly thing. And in fact, now you get an extra n here, but we got rid of the ugliness, so that's good. Once we have this expression, we can plug in n minus 1 for wherever there was an n, and the expression's still going to be true. That's just a variable substitution. So here we have, instead of n, we have n minus 1, n instead of n minus 1, n instead of n minus 1, n minus 1. We end up with this term here. What's interesting about that? Well, what's interesting about that is here we had a sum that goes to n. Here we have a sum that goes to n minus 1. If we subtract this from that, we get rid of the summation. Okay? Why is it? Well, it just is. Okay? If you want to believe it, do the algebra. Okay? But the trick here, I mean, if you see it, is to see that we've got sums that are basically identical. Okay? Except for the number of terms. So subtracting them, we've now got rid of the sum, which looks like progress. We've now only got 2t of n, well, basically a few t of n terms. Actually, 3t of n terms, but two of them are in n minus 1, one of them's in n. We can rearrange the terms to give us an expression that looks like this. T of n over n plus 1, t of n minus 1 over. What's the trick to see now? Well, if you look at it, this is n over n plus 1. This is n minus 1 over n. Both of them are of the form something over to the n over n plus 1. So we could rewrite this thing as a sub n equals a sub n minus 1, a to the n minus 1, plus this term. Which, if you think about it, if we keep adding, now we're just adding up previous terms. This is, in fact, just a summation. Okay? And when you look at what the summation is, you've got a 2, you've got n terms, you've got a I minus 1 over I. For large values of I, that basically cancels. What you're really left with is something that looks like 2 times 1 over I plus 1. Suddenly that harmonic number is coming out. This is, in fact, the harmonic numbers. So basically, a sub n is going to be equal to 2 log n. And since we were really interested in what the value of this thing was, in fact, a sub n is going to be n times this thing. Okay? Or the time that it takes is 2 times n log n. Okay, where that log is base e. In fact, this turns out to be 1.38 n binary log of n. Okay? So to get the exact bound, we're looking at, it's very little, it's only, n log n would be a perfect solution. In fact, it's only 38% more than if we always got perfect splits on average. Okay? So the neat thing from the analysis, we see just how good heap quicksort happens to be. If you don't understand the analysis, the important thing to see is all we did was solve this recurrence relation. The intuition for why it works is because we always got good splitters. Okay? And that's why quicksort is quick. Any questions? Okay, thanks for your attention. Pick up the next homework assignment, and I'll see you guys next class.